A $3 bait built from grocery store junk food reportedly outfishes live shad. Why would a fish ever choose this over real food? In some waters, even how you deploy it could cross a legal line. But the real explanation starts with a creature that tastes the world through its entire body. Human logic dictates that a wild predator like the channel catfish should prefer fresh, natural prey like a struggling shad over highly processed, factory-made meat. Yet across riverbanks, a persistent pattern remains. Anglers consistently report that cheap, high-fat hot dogs, specifically budget brands packed with sodium, outperform premium, lean beef varieties. While these informal comparisons lack the strict controls of rigorous head-to-head scientific testing, the field results are hard to ignore. Local variables like water temperature, current, and native forage density constantly shift the odds. This raises a fundamental question. When human standards of freshness do not apply, what does the fish actually value? And does dispersing this processed food to attract them cross the line into regulated chumming? To navigate rivers where visibility is often zero, the channel catfish relies on a sensory network that effectively turns its entire body into an exposed tongue. While humans possess around 10,000 taste buds confined strictly to the mouth, an adult channel catfish carries between 100,000 and 180,000. These taste buds are not hidden away. According to a review of fish taste systems by biologist Alexander Kasumian, these receptors blanket the skin, lips, and especially the 4 pairs of whisker-like barbels. As documented in T.J. Hara's research on fish chemoreception, these barbels act as physical extensions of the nervous system. They sweep through the water column, mapping out chemical signatures long before the fish makes physical contact with potential prey. The sensitivity of this system is extraordinarily precise. Electrophysiological studies led by John Caprio revealed that the catfish's external taste receptors can detect certain amino acids like L-alanine at concentrations as low as 10 to the minus 11.5 molar. To put this in perspective, this is a concentration so minuscule that it equates to detecting a few scattered molecules dissolved among billions of others, far below any threshold of conscious human detection. The olfactory system, housed in folded nasal cavities containing over 140 lamellar folds, is equally acute, picking up amino acids at picomolar levels. This dual-layered system divides the labor of tracking. Long-range olfaction identifies a distant scent plume drifting in the current, prompting the catfish to search upstream. Once the fish draws close, its external taste receptors take over, allowing it to taste the water and pinpoint the exact source. However, sensory detection is not the same as dietary preference. Sensing a chemical footprint merely alerts the fish that something organic is nearby. The decision to actually swallow depends on what happens when those thousands of external receptors encounter the substance itself. When a processed meat bait submerges, it triggers a sequence of distinct chemical reactions dictated by the laws of fluid dynamics and solubility. Sodium chloride and sugars, highly soluble in fresh water, dissolve almost instantly. Rather than projecting a distant olfactory signal, these dissolved molecules flood the immediate boundary layer of the bait. They alter the localized water chemistry, appealing directly to the catfish's close-range external taste buds. While sugars provide a minor gustatory cue, the sudden rise in salt concentration creates an osmotic gradient that makes the surrounding water taste intensely of dissolved nutrients. Unlike these soluble elements, the lipid phase behaves differently. Animal fats do not dissolve in water. Instead, they remain a separate semi-solid matrix. This fat acts as a physical anchor, slowing down the erosion of the bait while trapping volatile organic compounds. As currents brush against this fatty barrier, microscopic droplets detach and suspend in the water, carrying lipophilic odorants along with them. This fat matrix functions as a slow-release engine, ensuring the bait does not quickly wash away. If garlic is introduced, a complex organosulfur reaction begins. According to chemist Eric Bloch, crushing garlic damages its cellular tissue, causing the enzyme alliinase to convert alliin into allicin. Once underwater, this highly unstable allicin rapidly breaks down into oil-soluble diallyl trisulfide and other volatile sulfur compounds. For a scent-oriented predator, this chemical breakdown creates a highly conspicuous, pungent contrast caused against the natural organic backdrop of the riverbed, acting as a highly detectable chemical signature. This chemical mixture does not disperse as a uniform expanding cloud. Atema's research on aquatic plume tracking demonstrates that current and turbulence shatter scent trails into chaotic, intermittent filaments. A tracking catfish does not swim along a smooth gradient of increasing concentration. Instead, it encounters the bait signature as rapid, successive pulses. By analyzing the timing and arrival of these chemical filaments across its barbels, the catfish maps the turbulent flow, working its way upstream toward the origin. As the fish draws near, secondary visual cues come into play. In murky river environments, bright red or orange dyes scatter the limited downwelling light, offering a high-contrast visual target at close range. Once the channel catfish tracks the chemical trail to its source, the sensory input triggers an immediate behavioral choice. As opportunistic bottom feeders with broad dietary flexibility, these fish operate on a practical evolutionary strategy. If an object constantly tastes like food, it is worth eating. This contrasts sharply with visual selective predators like largemouth bass, which rely on precise cues like shape, movement, or living prey recognition before they strike. For the catfish, the sheer persistence of a detectable signal is enough to promise a caloric reward. This divergence in perception also explains why turtles often ignore the processed bait. Rather than a universal rule of the river, this disregard is species-specific, heavily shaped by season, turtle species, hunger, and local conditions. While a catfish decodes the murky water through an extensive chemical lens, turtles prioritize movement and visual shape. An inert processed meat chunk carries a distinct meaning to a reptile, leaving the durable, slow-dissolving bait to the specialized scavengers. Human concepts of food quality fail to predict what attracts a scent-driven predator. Premium meats selected for lean composition and lack of preservatives make poor baits because they release weak, fleeting chemical signals. Instead, cheap processed options accidentally combine high-fat durability with intense artificial markers. For a hunting catfish, evolutionary success relies on finding usable energy with minimal time and effort. This bait operates as a persistent broadcast signal rather than a superior meal. While natural prey still wins under specific ecological conditions, a durable, high-calorie resource is simply too profitable for a scavenger to ignore. Spreading processed bait sits on a distinct legal boundary. State agencies categorize hook baits and deliberately disperse chum differently, with definitions and enforcement varying by waterway, species, and method. Kentucky, under Administrative Regulation KRS 301001201, bans catfish chumming entirely, whereas North Carolina allows it, and Texas restricts transport between public waters. Food chemistry and deployment legality remain separate issues, meaning anglers must consult local wildlife agencies rather than assuming nationwide rules. This focus on environmental protection exposes the popular myth of WD-40. Anglers have long claimed the spray attracts fish, but official product safety data sheets reveal a petroleum-based mixture of mineral spirits and hydrocarbons, containing absolutely no fish oil. Humans easily detect the chemical odor, but controlled research shows no evidence that fish find it attractive. Spraying petroleum on a hook is an environmental hazard that violates clean water laws, rather than a secret fishing shortcut. The catfish's chemical receptors are tuned to organic nutrition instead of industrial lubricants. Subscribe to explore the science of the outdoors. Ultimately, the water we look at is far more sophisticated than we realize. As modern science continues to map aquatic chemistry, we discover that what seems like a simple feeding decision is actually a complex sensory negotiation. The riverbed remains a world governed not by human logic but by evolutionary physics.